screen, so hopefully we don't get sore necks. As far as the read, I kept the same, anticipating you're focusing on tomorrow night and not reading, which is okay. There's still that one extra credit item that's open. 2 of the items within close down tomorrow night at 5:30. That is the pre-exam survey and the study packet. Those links are found in campus announcements. As far as the third one, that opens up Friday morning at 6 a.m. and closes on Sunday for that post-exam survey, the one that usually gets forgotten about, so don't forget about it. Do it right away. Lab, how's lab going this week? You going good so far? Got some thumbs up? Okay. For those of you who still have lab, don't forget, you do need to have a procedure that's sufficient to conduct the experiment and have attempted answers at your pre-lab assignment questions. You can always change your answers or fix them before you turn in your lab report. We have a quiz on Friday, and that's one thing I was fiddling with behind the scenes here because I had accidentally put in your reminder the stuff for my 104 class, and I don't think you left my regular quiz. So, our reminder is open. This is student view. So there's nomenclature, there's using Avogadro's number, it is a calculation, and then there is writing ionic formulas and using the formula to determine the mass of one element given the mass of another element present. So 2 calculations, something about nomenclature, 3 questions if you ask, but one of them is multi-part. Are there any questions about that? And don't forget, it is a group quiz. 4 names maximum on each piece of paper, but groups can talk to each other. It's supposed to be a little fun. We good? So let me get out of here before I forget. Leave student view. We also, have the exam on Thursday. So as a reminder, I did shorten the end of the exam material to 3.5 because after I wrote it, I'm like, I just didn't want to put the stuff we're going to talk about today on there. That means exam 2 will start with the stuff that we're talking about today. Assigned problems, a couple of them in the lecture activity book. Some of them were the ones that I scratched off last time and put back, and then there's also page 88. In addition, there are some little exam 1 and 4 problems. I'm assuming, since this is for today's stuff, you probably won't look at it until after the exam, which is perfectly okay. Do you have any questions? Good? So then we're starting up. On page 4, I said number 42 technically, but I'm going to back up a little bit just to remind ourselves where we left off. So on, where are we? Number 39 and 40, they're just reminding us that chemical formulas are giving us the ratios of the atoms of each element to each other. I'm going to zoom this in. Not that far. Well, can focus, not that bad. There we go. So that's what those formulas are telling us, which is why, when we're doing a calculation to find an empirical formula, we need to find a mole ratio. That is our goal, to find that mole ratio. I will be putting the writing on the center screen, so there'll be a little bit of it more than usual today. So the path vertically, I also kind of wrote horizontally, just so you know, and that's kind of, I want to remind you about the formulas, and then we're going to put that in the center this time, because we don't really need the slide at the moment, that's all the slide says. And the next slide only has that table that has the bottom of page 80, so there's nothing really special on that slide either. So to go from percent to mass, we're going to use a logical sample size that makes life easy. What's percent out again? 100. So to do this step right here, we're going to use a 100-gram sample. That way, if we have something that's say 50%, well, on 100 grams, that would be 50 grams. The number stays the same, we just take off the percent sign, and we'll put on a G for grams. To go from mass to moles, we're going to be using the mole mass for the element we're thinking of. To go from moles to a mole ratio, at this point we have moles of 2 things, we're going to divide, and the easiest way to get hopefully a whole number is to divide by the smallest number. So here, divide by the smallest. You'll see when we do a practice problem. And therefore, to go from a mole ratio to the empirical formula, we're going to make sure that we're going to have whole number integers if needed, get them to be whole numbers, but then we're just going from a mathematical ratio to a chemical ratio. So check for whole number integers, sorry, subscripts. I'll just write check for whole numbers. one sample size is 100 grams, the other one is 1 gram. We're going to go through this on the table with 100 grams, and if you want to use the other side to practice, feel free. You should get the same answer, but then you'll actually have to calculate the 1 gram sample size and the percent that you have to find the new masses for the elements instead of just chopping off a percent and putting a G on it. So we can see that we have a compound that's comprised of carbon and hydrogen. Our carbon, we're told, is 84.09%. And our hydrogen, as we're told, is 15.92. So that's just our starting point. I'm just going to be writing underneath, and now it looks really, really large, and I'm going to have to constantly move my paper, so I'm going to just tap out a little bit. Give us a little bit more room. There we go. You can start whichever one you want, but I'm just going down. So carbon, 84.09% simply turns into 84.09 grams when we're assuming a 100 gram sample. To find the moles, we know that carbon's molar mass is 12.01 grams per mole. So for every 1 mole of carbon, we'll have 12.01 grams of carbon. This will give us the moles of carbon to be equal to 7. And then we go through that process with the hydrogen. We need both of them to make our mole ratio. So for our hydrogen, 15.92% turns into 15.92 grams of a 100 gram sample. Our molar mass for 1 mole of hydrogen, we have a mass of 1.01 grams. And when we take our 15.92 and divide by 1.01, we find our moles of hydrogen to be 15.76. Now, although the problem of finding the empirical formula is not testable material, these things are. So I'm just going to pause for a second if you have any questions. Hopefully they're simple, but time to ask. Yes?
You said it's not pledging.
The problem to find the empirical formula from percent composition data is not testable material.
Testable material.
Okay, sorry about that. But the steps we've done are. So whether we're using what we learned before to do something new. To find our mole ratio, we're just going to divide by the smallest. So the smallest amount of moles is 7 moles of carbon. So I'm going to be taking hydrogen over carbon. That would be 7 moles of carbon divided by, sorry, I flipped it in my head. Hydrogen over carbon. That would be 15.76 moles of hydrogen divided by 7 moles of carbon, and this will give us a ratio of hydrogen to carbon to be equal to 2.25 to 1. When you divide 15.76 by 7, you get an answer in your calculator of 2.25. Well, what's in the denominator? 1. Well, that cannot, you can write it as a formula, but it wouldn't make any sense. C1H2.25. So we are taking the step of checking for whole numbers. We don't have them. So what do I have to do to get whole numbers? Well, I think I've heard of 4. You take 2.25, it's 2 1/4. If you multiply that by 4, you get rid of the quarter. So if we multiply both the numerator and the denominator by 4, because we keep the ratio the same, that will give us our ratio of 9 hydrogens for every 4 carbons. That we could write as a chemical formula. C4H9. That would be an empirical formula. It's not telling us the exact numbers of carbon and hydrogen present, but it is telling us the ratio of carbon to hydrogen that's present.
Would you be marked off if you did H first? Like H9?
Not technically, yes, because you don't have enough understanding behind you. Okay? So right now, no, you're not. You'll gain that over time. Anybody else? So again, if you want to do the other side of that table, for 1 gram, you should get the same answer. Any questions? The next slide simply has the statement from number 44. That's all it says, so I'm just going to leave this in the center still. How are molecular and empirical formulas related? Well, the empirical is reduced from the molecular. Well, if we we reduce or we divide, right? Well, if we wanted to go in the opposite direction, meaning wanting to find the actual molecular formula, the actual numbers of atoms of everything present, we would have to multiply. I call this multiplication step a multiplier, as you can also see is typed in number 45. So they're asking us to write the formula for hexane as an empirical formula and then with a multiplier. Well, let's do it the way it's a little simpler for most brains. We have our hexane, our C6H14. If we want to go to the empirical formula, we have to divide each of our subscripts by some common number to reduce it. What can I reduce this down by? They're both divisible by 2. They're even numbers, right? So if I divide by 2, I will get C3H7. We would check again to make sure it's still reduced all the way. It is. I can't divide them down farther. And that, therefore, would be our empirical formula. The multiplier to go back will be times 2. Our multiplier would be 2, the number 2. There's a nice way to find this multiplier. If we know the molar mass of the molecule itself, we can use that along with the molar mass of the empirical formula to find our multiplier. I'm going to write that as an equation. This is where this other M comes to play. From the last time I talked about my MM, for a reason I don't use the M. Because we have this multiplier. I put this one in quotes. You don't have to. Just we're trying to keep it straight in our head. To find this multiplier, like this 2 here, we can take the molar mass of the molecular formula and divide that by the molar mass of the empirical formula. If we divide it by 2 to get down, and we multiply 2 to get back up, the difference in their masses as far as the ratio would be a factor of 2. Because we're keeping the ratio of the atoms of each element to each other the same. It's just the numbers of them are going down by some factor, but that also would change the weight by the same factor. They ask us to do this for our empirical formula that we found. So for example, in number 43, the molar mass is 114.26. That's the molar mass of the molecular formula. To find our multiplier, we need to find the molar mass of our empirical formula. So as they're saying, I just want to make sure it's clear, the molar mass of the molecular formula, I'm sorry, I got a little sloppy there, we're told is 114.26. There is no reason for them to give you the molar mass of the empirical formula because, and I didn't show too far, we have it here. We can calculate that. So, to calculate that, we would take 4 times the molar mass of carbon. To that, we would add 9 times the molar mass of hydrogen. And we would get 57.13 grams per mole. If you're ever unsure, wait, which molar mass they give me? Well, calculate the molar mass of empirical formula and see if that's what they gave. All we have to do now is divide these two, putting the bigger one in the numerator, the smaller one in the denominator, to find what factor we need to multiply our subscripts by to get our molecular formula. Get close to the bottom, okay, squeeze that in. So our multiplier is going to be equal to molecular formula on top, 114.26 grams per mole. Empirical formula on the bottom, 57.13 grams per mole. And when we divide this out, we get a number that's really close to 2. When you're doing this, if you get something like 1.95, just round it to 2. If you get something like 2.05, just round it down to 2. Okay? Meaning, our molecular formula is twice as big as our empirical formula. We had C4H9. If we multiply back to the center screen on the PowerPoint for a moment, because we have an image to look at, and it's color on the PowerPoint, and you have black and white on number 47. So, we're going to look at another way of finding empirical formula, and this is actually how it's done experimentally. Using this apparatus, we can put a sample of usually a hydrocarbon in that little yellow, looks like a wave out there. We infuse oxygen into this, and we basically heat it up until it combusts. And then we collect the products with substances that are specifically absorb either water and then CO2. I'm going to write the generic reaction, and we're going to talk about it a little bit. So, hydrocarbons are compounds that contain carbon and hydrogen, whereas hydrocarbon derivatives are compounds that contain carbon, hydrogen, and something else. We're assuming that we're possibly, possibly starting with the derivative. So I wrote a formula of CXHYOZ. We need to basically find out what the subscripts are using the experimental data. We're burning this in oxygen. We're collecting water and carbon dioxide. We're told that we have a sample that has a mass of 12.75 grams. It's combusted in oxygen, and it produces 34.96 grams of carbon dioxide and 28.63 grams of water. We're going to use that information to find that empirical formula. I just switched the paper to the center again so that we'll be able to work with that. I'm just writing down my amounts. So I have 12.75 grams of my sample. It was 34.96 grams of carbon dioxide. And our water was 28.63. I know it's on the next page. The next page steps you through the process. My slides basically just had these steps as they're already written out or typed out for you. My slides also had the image of the apparatus on them. So we're going to consider these products, and we're going to think about, from our reaction, where is every part of our molecule showing up in the products. The only place the carbon from the fuel can go to is the carbon dioxide. So we can use the mass of carbon dioxide collected to find out the mass of carbon that was present in the original compound. That's what we're doing in part A. So we have 34.96 grams of carbon dioxide. We'll have to get this to moles to break apart the carbon from the oxygen and the carbon dioxide. So every 1 mole of CO2 has a molar mass of 44.01 grams. We can see in the formula that for every mole of CO2, we have 1 mole of carbon. And I know it doesn't change the math this time, but other times it could. So you get in the habit of actually writing your ratios when it's 1 to 1, then you don't forget to write the ratios when it's not 1 to 1. To find the mass of carbon, now we can just use our molar mass of carbon. 12.01 grams for every 1 mole of carbon. When we calculate this, will tell us we have 9.54 grams of carbon in the carbon dioxide, which means there's 9.54 grams of carbon in the fuel. The only place the carbon can go. Any questions about that calculation? Because that is testable. It's just the whole
has to be the same as both.
Yes.
Right, got it.
We can't lose hydrogen, right?
Right.
Law of conservation of mass. Could we use the same process to find the oxygen? Could we find the mass of oxygen in the water and the mass of oxygen in the carbon dioxide and add them together and say that's the mass of oxygen in the fuel? Hopefully you're saying no, because we have O2 also. So it means we need to use a different method, and that question that was just asked actually brought up the reason why we're going to do this a different way. Law of conservation of mass. I know the total sample size for the fuel. I now know the mass of carbon and hydrogen. If I do just simple subtraction and I have leftover matter, it had to have been the oxygen. So for part C, using law of conservation of mass, 12.75 is the total. From this, I'm going to subtract off the carbon, 9.54, and I'm going to subtract off the hydrogen, 3.21. When we do this, we have nothing left over, meaning there is no oxygen in the fuel. I just dropped up the OZ, meaning now we're just dealing with a true hydrocarbon. We still have to find out what X and Y are. Notice we have masses for our elements. In our last problem, we started with percents, but we turned those to masses right away by assuming a 100-gram sample. Well, we have the masses, and these masses are for our 12.75-gram sample. There's no reason to back up to percent. We have masses. We can go to moles, and then we can make a mole ratio and find our subscripts. Just going to have to bump the reaction up a little bit. So for part D, we know we have 9.54 grams of carbon. We know we have 3.21 grams of hydrogen. The step after the mass was the mole. So for our carbon, 1 mole has a mass of 12.01 grams. And this will give us 0.794 moles of carbon. For our hydrogen, 1 mole has a mass of 1.01. And this will give us 3.18 moles of hydrogen. Those moles are for the 12.75 gram sample. We need to relate them to each other, make our mole ratio. Divide by the smallest. So we're going to have 3.18 moles of hydrogen divided by 0.794 moles of carbon. And when we divide this out, we get 4 hydrogen for every 1 carbon. We have whole numbers, meaning we don't have to multiply by something like we did last time. Oops, almost went off the edge. There we go. Any questions? I still see people writing, so I'm trying to stop. The page 83 is on the lecture activity list. Don't forget when you come across block review pages, I'm not assigning them, but if you are very curious and want to do them, all you have to do is send me an email. I can send you a picture of my work. See if you got them right. If you wanted to try them. Meaning we're moving on to section 3.7. Any questions before we then? We'll be going back to the PowerPoint. No, that's not a laptop. We do a brief review on chemical equations. So when we're writing a balanced chemical equation, it should of course be reviewed for you, but our reactants are on the left-hand side, our products are on the right-hand side. Notice it is an arrow, not an equal sign. I will actually deduct for students who write, for example, reactants equals products, because they don't, right? The arrow is signaling a process that's occurring. If you take Gen Chem 2, which most of you probably are, but maybe not all, you'll learn a lot more about that process. They are not equal. The only way that they're equal is in terms of carbons don't have to be next to each other, they still count, so we have 2 carbons there. We also have 3, and a split one over here, 4 hydrogens, and we have 2 oxygens. I'll put the XY after so you don't think 20. If we want to put a coefficient in front of that, such as a 2, then of course it's just increasing the number of all the atoms of the different elements without changing what the molecule or chemical formula is. So 4 carbons, 8 hydrogens, and 4 oxygens. We can't change the chemical formula for our reactants and products because then they have to have different properties. So the way that we increase the amount is by using coefficients. Questions? We also need to be able to balance for mass and charge. And you probably in the past, I'm assuming you've balanced for mass, but you might not have thought about charge, and that's actually really important in chapter 4. So they have 2 examples for you, and hopefully it makes sense for the Roman numeral I, that the first one is unbalanced, although it's labeled unbalanced. A carbon monoxide CO plus an O2 does not just give us a carbon dioxide because we have lost an oxygen atom. So therefore, we need to make sure that we have the same number of atoms of each element on each side of the arrow. By putting a 2 in front of the CO, that increases our number of carbon and oxygen, meaning we also need a 2 in front of the CO2. If you count now, you can see we have 2 carbons on each side of the arrow, and we have 4 oxygens on each side of the arrow. The one for charge, I actually want to write a little bit about. Because students get confused when it comes to charge. It is balancing for mass as well, but you don't really see what's going on with the mass. So the one you have unlabeled is Cr plus Sn2 plus going to Cr3 plus Sn. And some students see that as being balanced. There's a Cr on each side, there's an Sn on each side. How is that not balanced? Well, to make the chromium 3 ion, the chromium had to have lost 3 electrons. Right, that's how it becomes Cr3 plus. Well, for the tin 2 plus to become a tin atom, the tin 2 plus has to gain 2 electrons. And there, hopefully we can see we've lost or gained an electron. If one loses 3 and only gains 2, where's the other electron? We call it balancing for charge, so that it's easier for Gen Chem 1 students, but I'm helping you see that it really is matter that we're losing or gaining. The one that is labeled balanced has the 2 Cr plus 3 Sn2 plus going to 2 Cr3 plus 3 Sn. If we have 2 chromium atoms becoming 2 chromium ions, there has to be a loss of 6 electrons. 3 tin 2 pluses becoming 3 tin atoms, there's a gain of 6 electrons. Now we have conserved all of our matter, even the matter that we really don't count for mass, those tiny, tiny electrons. The charge part is, on this side, the reactants were plus 2, right? Neutral atom with plus 2. On the other side, the products were plus 3 ion with a neutral atom. Now we have 3 times 2 plus would be 6 plus on the reactor side, and we have 6 plus on the product side. So whichever way is easier for you to see. You can either think of it as mass, or you can think of it as charge. Any questions with that? And of course, when known, and so you'll be expected to know some of these, you have to have your states of matter. You should already know diatomics, right? We went through that in chapter 2. So a solid is parentheses with a lowercase s. Liquid is parentheses with a lowercase l. Gas is parentheses with a lowercase g. And aqueous means it's dissolved in water, AQ in parentheses. Hopefully that's not random. Any questions? This is copy and pasted out of your top page 87. You could be given chemical reactions in words, or you could just be given a the middle just to save some necks on that side of the room. So we have hydrogen and oxygen, and we're making water vapor. What's the formula for the hydrogen? H2. The 2 was what I was really listening for. We're also then combining that with oxygen. Is that monatomic or diatomic? Diatomic. And we're making water vapor. Hopefully we all know that water is H2O. And since they told us vapor, we know that that is a gas. Water can be in the vapor state or the liquid state at a given temperature. What's the state of matter of the hydrogen and the oxygen? Gas. Good. What do I have to do with balancing? How about the reactant side? Do I need to put a coefficient anywhere? In front of which one? Hydrogen? Okay. And what about the product side? Do we need to do anything? Oops, that's supposed to be a 2, sorry. Not an H. A 2 here also in here? Yes. By putting the 2 in front of the H2, we now have 4 hydrogen atoms, so hopefully we need the 2 over here. That actually helps our oxygens. We had a single one and we had a double one. Meaning we had 2 on one side, 1 on the other. When you have a diatomic present, you're forcing it to be even on one side of the arrow. If you have an odd on the other side of the arrow, often the nice first step is to get that odd one even. Meaning, I did start from the reactants for a reason, to show that sometimes starting from the products can be very helpful. Even, odd. Oh, I gotta make that guy even. I put a 2 there. That helps, that balances my oxygen, but now I've increased the hydrogen, so you put a 2 there. So, diatomics, that's actually a really good technique sometimes to look for the odd one versus the evens. Double the odd one up right away, and that gets you going. What about our reaction of hydrogen and nitrogen to make gaseous ammonia? We already know the H2 is a gas. What's the formula for the N? N2 and state? Gas, okay. Ammonia is a common name. If it was a testable situation, or testing situation, I would actually either just give you the formula NH3, or I would use the nomenclature system, meaning nitrogen trihydride. I wouldn't expect you to necessarily know the common name. The only common name I would expect you to know is water for H2O. How about you take a moment and balance it? We'll have somebody just read from reactants to products our coefficients. Whenever you're ready, somebody has it, just say it. So did you say 3H2 plus 1N2 gives 2NH3? Good. They're not difficult ones. So 3, I'm going to put the 1 here because I just want to talk about it for a second. And 2. Kind of so lazy about their 1s. We often don't like writing the 1s, and you don't have to write the 1s unless the instructions for a question on a quiz or exam says, make sure to include all coefficients even 1s. Because we're testing to make sure you didn't just skip it, you didn't know it, or did you just assume it's 1? So you would be asked to put the 1s. However, I know some students like to always put the 1s, which is perfectly fine. You can do that. Just make sure to read instructions for questions carefully. And that will be like next week's quiz. Any questions so far? Got one more. So our last one is magnesium metal and oxygen that forms solid magnesium oxide. What's the elemental formula for magnesium? Mg, not Mn. That's manganese. And we already did the oxygen, so I'll put the O2 gas in. What about the formula for magnesium oxide? Did I hear MgO out there? Magnesium is group 2, so it'll be plus 2. Oxygen is group 6, so it'll be minus 2, so it's a 1-to-1 ratio, and we were told it's a solid. What would be the state of matter for the magnesium metal? Solid. What do I have to do to balance? Here, 2, 1, 2. A couple of different people are talking. There you go. I put the 1, it just makes them happy. You don't have to have the 1. Any questions? We do have some more images coming through. So I'm going to go back to the computer. So in number 2, and there's not a lot of this on this one, and it's really up to you if you want to do it, but we have to realize at least that we can think of balanced chemical equation in terms of the particle level, meaning molecules. We can also think of it macroscopically as far as moles. We'll talk about the masses less. So if you wanted to read this out on the particle level, you would say 3 hydrogen molecules and 1 nitrogen molecule react to produce 2 ammonia molecules or NH3. On the mole level, that would be 3 moles of hydrogen and 1 mole of nitrogen react to form 2 moles of ammonia or NH3. Can I say 3 grams of hydrogen and 1 gram of nitrogen combined to form 2 grams of ammonia? No. In terms of masses, we can still use the coefficients and balance, but we have to include the molar masses, right? Because if I simply said, and I know I already said this, 3 grams of H2 plus 1 gram of N2 combined to form 2 grams of NH3, we're assuming that all the atoms have the same mass. So we cannot do that. We could say 3 times the molar mass of hydrogen plus 1 times the molar mass of nitrogen can combine and form 2 times the molar mass of NH3. That's okay. But students often make the mistake in stoichiometry of using mass ratios without using molar mass. Any questions? The bottom statement is kind of just a place for you to think about balancing. We're going to move on to the next page, and this is where the visuals come in more into play. We're still looking at the production of ammonia reaction. So in number 3 it says, consider reactions of production of ammonia. Show this using particle diagram. I put up a particle diagram just to illustrate you could be asked to do a particle diagram for a chemical reaction. You actually aren't been asked to do that. Got to think about that. We did it for physical changes and chemical changes, right? So just a reminder that it could very well be done. What if you wanted to make 6 molecules of ammonia? Well, if each going through the reaction produces 2, I would then have to do it 3 times, right? To get 6 molecules of ammonia. If you're asked to do a particle diagram for a certain amount of product, yes, you could be asked to do that. So just make sure that everything is balanced and you haven't lost any atoms. Which representation of the balanced equation using chemical formulas or particular representation is most helpful in thinking about how the molecules interact to break bonds and form new bonds? That would be the particle level idea. You're seeing things being connected differently between reactants and products. Which representation is more helpful in calculating? That would be symbolic, of course, the balanced chemical equation. Do you have any questions? I did put 4 and 5, page 88, which is just a bunch of, 5 is like, I don't know how many, like 20 balancing practice from the textbook. So a bunch of practice balancing chemical reactions. Number 4, we kind of already talked about it, but you can't use mass ratios. You have to incorporate the molar masses. Does anybody have more than 1 exam this week? Just ask me. Couple? You know what? I want to stop. We're going to stop. I'm going to give you 7 minutes of your time from me. Yeah.